1. All right, local recording. You know, you work your butts off, but you're also for the most part, you're all responding to my feedback, and for the most part, you guys are making a sincere effort. And I think almost all of us have got at least an 85%, and most of us are more like 90% average at this point. And because I don't like grade really is on hard work and that you respond. So I think you guys are doing fine. Right. So this morning, of course, I got caught up as when I was younger. It was like going to the library, look up something in the encyclopedia, and then I would spend hours leafing through the encyclopedia, reading everything but what was supposed to be looked up. It's just fascinating. And I wanted to tie up some loose ends because I said it, well, in the videos I posted with you guys, I didn't get this far, but I did post a video on some thoughts. So I was playing with a spreadsheet, and then the other thing, I don't know if I showed you this thing, and I realized it was a mistake to say to you guys that well, when you change the sampling rate, you're letting in more and more noise. And so I was trying to figure out a way to show that to you, and I showed a picture with a little, well, you can't see, you can't see me, can you? I'm using my hands to talk, but you don't have the ability to see me. So I had this idea of saying, okay, there's a window, and depending on the sampling rate, and it's true, but I thought I began to realize it's just a little bit too much for you guys and I was trying to simplify it, and then I hit on this analysis here, and this is a particular sampling rate, 10 hertz. And you see that this 1 hertz wave can be nicely reproduced, and then a 2 hertz, 3 hertz, and you get to a 10 hertz wave and it can't be reproduced at all. So this is sort of the idea that as you open up, if you go to higher sampling rates, then you can get what happens is you start picking up more and more of the noise, because the noise is at higher and higher frequencies. You're letting more and more of it in. But I hit on a better way to think about it, and it was when I made these slides here, and I posted these. So what this has to do with what's called Nyquist theorem, and actually the Nyquist theorem says that you need to sample something at twice the rate, the frequency. So in the case of this guy, this is only a 1 hertz wave. Yeah, Adobe, somebody commented, sorry, Layla. Right. It just makes you don't have to like run over to a locker, and yeah, it's nice. It's a great idea. The kids in my 1,200 kids last spring, because I had downloaded several of them, and they were all using Adobe Scan. Anyways, so at 1 hertz, you should be able to get away with a 2 hertz scanning rate. And that's right, because what will happen is you get a dot here, a dot here, and a dot there, and here. So let's see, 1, 2, 3, 4. Well, that seems like I'm not doing it right, but for those, a 1 hertz sine wave. And if you know exactly the wave that you have, yeah, you can get away with a low sampling rate. However, though, I tried to emphasize that when you're looking at a signal, first of all, there's like even the blood pressure, right? It wasn't a sine wave, right? It's sort of this strange shape. And then the EKG had lots of crazy stuff in it, right? So I wanted to sort of emphasize by you see these dots, if they don't line up just right, you can get a pretty funky shape. But as you go up in sampling rate, now when you're at 10 times, then you see is even if these dots slide left and right a little bit, then you're always going to get the sine wave, even though the 4 times or the 6 times is okay, would do it. You have to allow that you might have, you're not going to have a uniform wave that you're sampling. And in fact, let's think about this. What would be and another mistake I made in the video, and when I was talking with the students on Friday, I was saying that let's see. Now I'm changing the order I'm doing things, but I'll get back to it. Okay. A heart rate, say they're 50 to 90 or 100 beats per minute. And so I was trying to say that was like 50 hertz, and that's not true. That's about 1 hertz to, because at 60 beats per minute, and then we divide by 60 seconds per minute, we get 1 beat per second. Now, if we look at the blood pressure curve, so this is about 1 second, and it's not uniform. So we kind of think we need to sample at 10 hertz. But even then, 10 hertz wasn't enough, right? So we decided that 50 hertz was better. Because what it turns out is that this is not a uniform sine wave. And oh yeah, guys, this is, I wouldn't sweat this stuff. If you don't understand it, don't worry about it. It's not important for a report or you write up anything. Just filling in some blanks, because in the way I believe and the way physicists believe is that when you understand simple underlying principles, it makes things easier to understand. Now, what I was saying now, in fact, the beginning of this thing is a little steeper, right? So it turns out that, think about different sine waves, that with a higher frequency, the beginning is going to be steeper. So this represents, this little slice right here, this represents greater than 1 hertz. So this is why we would think we need something like a 50 hertz sampling rate. Let's say this is more like 5 hertz or more like 10 hertz. So the theory says you need to have twice that much. But for us in general, we like this idea of 10 dots, at least several dots, so maybe like 10 dots over this thing. And in fact, this was 50 dots. Okay, good. So then we divide it into sections. And it's hard to be quantitative because the math is really deep. But we like the idea of 50 hertz, and it worked really well. And it let us see all the little wiggles, because any little wiggle, any littler wiggle has the chance of being a higher frequency. Wiggle it corresponds to higher frequency. So that means we need a higher sampling rate. So we figured 50 hertz, we saw what we wanted to see for the blood pressure. Now this next animated GIF is kind of cool, but it'll drive you nuts after a while. But I made a screenshot of it. So this is the example here that you have to sample enough times. So because you see some of these guys have steeper rise times than other ones, so that means they're higher frequency. And so once you get, what happens is, what they're saying is that from 0 to here, this is the max frequency in this. This is showing us how that, like at this frequency, there's several wiggles there, but there's still some wiggles that have very, very short wavelengths in here. And so you have to figure out what's the max frequency, and then the sampling rate is equal to 2 times the max frequency. And that is, I'm not sure if it's right here or if it's right there, but you do see when you get there, you've got this thing, right? And one thing to notice, and I talked about it offhandedly, was that you notice the narrow things. The narrower something has, the less amount of dots it has. So I decided, okay, I'm going to say that right about here, it's about 9 omega. And I thought, okay, 3 times pi is 9.42, so that's about here. And I guess I should have sent you these slides. Well, because you really need these things if you're interested. Let's see, PDF. Let's hope it doesn't make too big of a PDF. Every time I write something on it, it gets really big. And, oh, it's not so bad. 900 kilobytes. Okay. Because you'll never have time to write this down as I'm. But you can make little notes to yourself, and again, you don't have to if you don't want to. But now at least you can make little notes to yourself. This is for slide 1, slide 2, slide 3. See, next time I do this lab, I'll have it all kind of packaged up better. Okay, so just to make my life easier, because I know omega equals 2 pi times the frequency, I'll say that this is omega, the highest frequency is omega equals to 3 pi, about 9.42. So then 3 pi equals 2 pi f, and the pi's cancel out, so f equals 3 halves, and hertz. So this says that I should sample at 3 hertz, twice that. And I've been trying, they didn't give me any associated numbers with this. So I drew these 2 blue lines on here. And if you squint your eyes, 3 hertz means that every dot should be 0.33 seconds apart. So then what I did is I used a snipping tool to zoom in. And in fact, that pretty much looks like it, right? it looks just like 1/3, 2/3. So it looks like 1/3. Oh boy. Looks like 1/3 of a second, or 0.33 seconds. It's just hard for me to say where is the place where this high frequency is. And how could I draw a window around it? I got to get a spreadsheet going on so I can figure it out. Well, I can see, right here. See this right here. If I wasn't sampling it like that, I wouldn't see that. There you go. Okay. Very good. There it is. Now I got it. See, when we talk to each other, I mean, okay, I'm doing most of the talking, but this is why over my whole professional life, I love explaining things to people, as I learn so much personally when I explain things. So then, let's take a look at the EKG. So this is our actual data after we put the moving average on it. And what you see is that there's point from one place to the major lines are 0.1 seconds. Excuse me. And the little lines are 0.02 seconds. And you see that if I were to put a dot at every one of those, I can easily see the EKG. The reason we see lots of it is because we did this thing called a moving average. And so we still get that many points. And I was trying to show you what a different kind of averaging technique that you would use here. In that spreadsheet I showed you a glance of. But, at the end of the day, it just ran out of time, and this is good enough. This explanation, I think you can see that. And then if you take 0.02 and do 1 over it, you end up with 50 hertz. And in fact, I better verify that, because I have a tendency to just think I can do these things in my head all the time. Yeah, it's 50. So that's why 50 hertz worked for the blood pressure. I didn't put a blood pressure plot up there, but here's the EKG. Now, the trouble is that when we did 50 hertz sampling, the 50 hertz, just didn't work. And we could have done 250. 250 seemed okay. But the reason we picked 500 is that when we played with the trend lines, we saw that when we played with the trouble is that the software, the Capstone software, did this funky kind of sampling, averaging. But I played with the trend lines ahead of time, and I knew that it was going to be about 8 to 10 on the moving average. So what happens is then, effectively, we end up with an effective 50 hertz sampling rate. And I didn't do a great job of explaining that up till now. And I think I've got it. Come on. Why don't you want to do this? Doesn't want to erase. I want to rewrite this. Oops, well, that's something. There we go. So we get an effective 50 hertz. That doesn't look much better, right? E, F, F, E, C. Whenever I'm at the bottom of the page like this on the tablet, my wrist is like hanging off the desk. It's hard to write neatly. You know, if you divide by 8, you're getting more like about 60 hertz. But you're in the 50 to 60 range when you divide by 8, when you use the 8 to 10 average. And that's why we picked 500 hertz. And it's pretty straightforward. I finally, for me, it was a question of, I've been doing this so many years that it's so deeply in my head that I had trouble getting it out, and I knew it, and I had some fits and starts on this, but this basically I think ties it up with a bow. Okay, so in fact I'm going to stop my